presentation starts after that. So, hello everyone. Hope you're all doing well. I'm Ahmed Maghri, computer science major and mathematical minor, and president of the Math Society. And this is Loredana Jacob, CVT major, and also the co-president with me of the Math Society. Today is I would say, a very important day. We have the undergraduate seminar 3. But what's the undergraduate seminar? That's a very, I would say, important question, right? So,
the other.
No. Sorry, guys.
I didn't bring my mouse, I'm sorry.
Where's the mouse? Okay, the other side. What?
Okay, sorry, it worked like 5 minutes ago.
Yeah. So, to continue, what's the undergraduate seminar? So originally, the undergrad seminar for CPCT, we're going to call it UGS. So UGS was initially a model for math majors, where they have to prepare some research, then present it in front of their cohorts. But, you know, Lagos University, now it's Construction University, a lot of changes, and then decided to remove the undergrad seminar from the math majors' curriculum. But us, the Math Society, decided to bring it back to life. So the concept of the undergrad seminar is that we give 3 selected students the opportunity for during 3 weeks to do the research, to prepare it with us, their supervisors, and to make the paper officially reviewed and finally get published. And today is their day, because today is going to give you the motivation and give you the envy to read the papers.
The first 2 undergraduate seminars were last year. 6 papers were written in total, and this year we started with the next 3. The first one presented today is Natia's. She wrote a paper on dynamics of string theory. She's only a first year and she was already able to write a paper on this topic. You will see a lot of advanced physics and how it's applied in physics. Next one is going to be Zacharias, also a first year, and he already wrote the paper. And he is going to show us how mathematically we can write an algorithm that describes the water flow in irrigation and drone use. And last but not least, Noah, a third-year physics student, not PhD.
Physics and data science.
Physics and data science. You probably know him already. He is going to explain us how mini-golf works using Lagrange mechanics. Lagrangian mechanics is some very advanced type of mathematics or physics that explains this, that explains geometry. And yeah, he's going to show you how this is going to work in mini golf. You're going to start with them in a few moments, but before that, we would like you to apply for maybe the next event. If you are interested in writing such a paper under our supervision, or just write a paper and make a presentation on a topic, you can apply here for the next undergraduate seminar, which is hopefully going to be next month. But we're also looking for board members, for people in PR who help us with writing posters and bring more people to our events. And also you can find us on WhatsApp and Instagram, so scan those QR codes and follow us.
So please be ready, because in a few minutes, we'll start our first talk, Dynamics of String Theory, given by Natia. Thank you very much. No, this one is actually PhDS, and the H is smaller. Like it's actually the right one. I just forgot to write it S. It's forward and this is the latest one. Like imagine the slide's going now.
I really turned the board also. Yes, you have the pen now, and you can write the camera. It's already turned on? So we'll remove this, right? Yes.
Give me the answer. It'll just be
Too much.
Okay, I hope everyone is ready because I'm going to start. Thanks first of all for coming. So I'm Natia and today I'm going to talk about the dynamics of string theory. So the main of my paper and my talk in this case is to make the readers or listeners understand the basic concepts of string theory. So what is this theory? Where does it come from? Like, what's the history behind it? And why is it important for us? Why does it unify all of physics? So what's theory of everything? You might have heard of it if you're into the science, maybe on the surface level, but at the end of this presentation you'll gain the fundamental concepts of it. But I'm going to spoil you a little bit just so we understand what we're talking about. So basically, string theory is the theory that might unify all of physics. So it might unify the particle physics as well as general theory of relativity. We have two types of strings, open and closed, and basically their interaction, it might explain the unification of physics. So basically everything that's happening around. Okay, so first of all, let's start from the history. Where did it come from? So in 20th century, physics, it was shaped by general theory of relativity, which explains basically the curvature of space and the dynamics of space. And it was also shaped by particle physics. So basically every single particle in force except for gravity. And there were many physicists ever since trying to kind of unify all of these concepts into one theory. And some of them were more successful than others. For example, string theory was kind of a booming one. That's what we're going to talk about. So where did it give rise from? The string theory first emerged in the 1960s when there was a hadron experiment. Basically, hadrons are particles like neutrons and protons, and when they collided, there was a very interesting outcome. Either a virtual particle just emerged from the collision, from their interaction, or it was exchanged. Already existing virtual particle was exchanged between the hadrons. And this could be explained if something was happening in the fundamental particles themselves, something happening inside. For example, string theory is vibrating strings. So the strings inside the particles are made out of strings, and the vibration of the strings, so the vibrational mode, it corresponds to different particles. So that's how strings emerged. It's basically a one-dimensional vibrating string, and the vibration mode, again, corresponds to different kind of particles we have. Also, it's important to note that string theory is not like basically a one-dimensional string, it's a wave. We're going to talk about that in the upcoming slides, but just so you have a quite understanding. And also, it gives rise to theory of everything, because we have two types of strings, open and closed. And closed strings vibration modes, they correspond to a graviton. So by interaction of closed and open strings, you can actually understand the unification of all processes happening. And that's our end goal today, so that's our destination. We're going to talk about different string types, what strings are, and there's some quantum properties. And after that, we're going to talk about the unification of strings, so how they interact with each other. Okay, so before we start the mathematical part, it's not too scary, honestly, because it's mostly conceptual in my talk, but still, we have to walk through some of the terms we have. So first is the worldsheet. Every calculation that we're going to do, it's not going to be multidimensional, because you probably heard that, oh, string theory is like 10 plus 1 dimensions, is probably very complicated stuff, but it's really not that hard. We just take the worldsheet. It's a surface that a string swipes out while it's moving, and then we do calculations on that worldsheet and we implement it into higher dimensions, so it's not that hard. Next, a D-brane. So basically, when we have a string, can I turn on the whiteboard? How do I do it?
Just take the pen and press it.
Okay, just press it here.
Yeah. Annotate.
Whiteboard.
Annotate.
Do you want to use the slide or you want it to be white?
Just want to white. Okay, it doesn't matter. So we're going to talk about types of strings, but when we have a string,
Just the color of the white, maybe.
how do I do this stuff, guys? Okay.
It's on below.
Yeah.
We're going to talk about types of strings a little bit later, but when we have a string, an open string, its ends can be attached to D-brane. So it's basically a surface we're talking about when we're talking about conditions of boundaries of open and closed strings. So it's basically a property that's bound to the open string. Can I just use this whiteboard? That's fine. And next is Minkowski spacetime. In my paper, I use this term a lot, but it's basically just a fancy term for D-1 spatial dimensions, and we also have one for time. Okay, embedding into the spacetime. So I talked about worldsheet, and it's important to understand what's the formulation, like how do we do the computations and how we do take it to the multidimensional world we're talking about. So we have coordinates. We can say we have alpha 1, alpha 2, and this can be written as r and alpha. This stands for time, and this stands for the position of a point along the string. And then how we do it, how we do the calculation. So basically we have x in the mu direction here, r, and some alpha. Then we have sigma. This stands for the worldsheet. So basically all the calculations that we're doing in the worldsheet, which is a two-dimensional surface. And then with some mathematical operators, we take it into the higher dimension. That's just the mathematics behind it, so you understand the frameworks, because every formula that we're going to use is just for a two-dimensional worldsheet and not actually this fancy multi-dimensional space. Okay, now let's talk about string types in general. We have two types of strings, as I've told you. We have open and closed. So open strings, they correspond to gauge forces, like all types of interactions forces we have except for gravity. And closed string, they correspond to particles like gravitons. That's why we're trying to discuss their interactions in order to understand theory of everything. So the unification of all forces except gravity, then we have particles, of course, because particles emerge from strings vibrations, and then we have gravity, quantized gravity particle, which is a graviton. We have two types of open strings. We have the one that I talked about when I was talking about D-branes. So we have an open string, and its ends are fixed, are bound to D-branes, so just some kind of surface. And then we have another one. This is Dirichlet's type of string. Then we have Neumann's string. It's just open. So this part, it behaves as a wave. We're going to get that into details in a few slides. But it can also freely move, so it's not attached to anything. And in closed string, it just forms a loop. So that's how you can imagine it. Closed string. Okay, now understanding the string motion. Can you delete this? How do we? Okay, thanks. So I was talking about how strings are actually waves. So it might be kind of hard to conceptually understand what strings are. They're described by this equation. So there might be a question like, why do we have closed strings, or why do we have open strings, and why do we have boundaries if it behaves as a wave? But it's basically just the boundaries for the wave. So for the closed string, we still have the boundaries, like it starts here, where x is equal to 0, it ends where x is equal to 12, but this part is just not how I draw it. It's not a straight line, just so you conceptually understand it. It behaves as a wave. This is the wave equation we have. U is the displacement, x is just some kind of position, c squared is the wave speed. And every formula from now on, we just derived from this wave equation. Okay, now let's talk about different boundary conditions. So I talked about having two types of strings, right? We have closed and open strings. Closed are for gravitons, open strings are for any other forces. The Dirichlet boundary condition is the first condition I was talking about, when you have an open string and its ends are just bound to some kind of a D-brane, some kind of a space. So they're fixed. This part, it can behave as a wave, but this part just stays fixed, it does not propagate in space. So here's the boundary condition. U is for the displacement. We have two conditions from the left side, where x is equal to 0, and from the right side is x is equal to L, from the left boundary and right boundary. This big U just tells you the fixed position of the ends of the string. So if it actually does not move, it does not oscillate, from both sides, this big U is going to be equal to 0. So this wave function, it acts accordingly to the ends. If ends are oscillating, if ends are fixed, it can be oscillating also like this moving boundary. Okay, also we have strings position. So in the upcoming formulas, at the end, for example, with the interaction of strings, it's important to understand just the basic concepts of movements of strings, because it's not only dependent on the static line and the position between the points, it's also dependent on this part, which is vibration oscillators. We're going to talk about that because that part is very important for string theory. It's almost in every formula. We're also going to talk about the mass formula for every particle, just to understand how particles emerge from strings and strings properties. And just keep that in mind that we have this part. This is just for string position. Let's just say it's distance between the lines, and this part is for vibration of strings. Okay. The next boundary condition we have is for open string is for Neumann. So the first we had, if you remember, it's an open string and it's bound to some kind of surface, a D-brane. For the second one, we have Neumann boundary condition, and it's just an open string. It acts as a wave. It's not bound to any surface. The ends are not bound, and it can just move freely in the space. So for this boundary condition, the thing that we have fixed that's constant is the derivative of displacement. So how the ends are curved at the boundaries for both left and right hand side. Okay, now moving to the interesting part, which is gravitons, closed strings. I've said that closed strings are just forming a loop, right? So for the position condition, we have that R and alpha. This is basically, I told you that that's position, but it's equal to the alpha, R alpha plus 2 pi, because it forms a loop, and the position at alpha is the same as 2 pi plus alpha. Okay, now this is my favorite part. I talked about the position of a string, right? And I told you that that it does not only depend on the distance between the lines, it's also dependent on the vibration of strings, right? It was the sum of some kind of vibration modes. This is dependent on the mu, which is a spatial direction. And this part is a node. So basically, we just take all points along the string and we add their vibrations, and it's dependent on the position of a string is dependent on this part. So this is just a mathematical operator, and you see it a lot in the upcoming formulas and pretty much in every formula, including the theory of everything. This is a mathematical operator, so you can extract it, you can add it. We have a creation operator, we have an annihilation operator. This is the creation one. When we put this dash, I hope you can see it, I'm sorry for this. This is an annihilation operator. So basically, I said that vibration is very important in string theory and for the movement of string theory, for the position formula, because we also talked about how vibrations give rise to different particles, right? So different vibrational mode is different particle. So once we've add or extract the vibration as the strings, we get this formula for different kind of particles. I hope you understand this part. Okay, now we're talking about mass. Why we have to talk about mass is because I told you that's a very neat formula, right? It looks not as complicated as it should. So it gives rise to different particles. So the vibration of strings and the strings properties give rise to different particles. And that's how you can calculate the mass of a particle according to the string's properties. So m squared is equal to 1 over a prime. A prime is string tension. It just tells you if a string is stiff, if a string is soft. It's just kind of a energy per unit area of a string. Then we have n, which is the excitation number, and it's just basically energy of a string. And then we have a, normal ordering constant. Why I told you that everything is bound to this small a we were talking about with the spatial direction and with this node and the creation and annihilation operator, because this basically rearranges creation and annihilation in order so it's not infinity. So it's quite hard to imagine, but just for your curiosity, once we measure the creation and annihilation operators for nth node, it turns out to be infinity. And at the end, when you put this infinity into the formula, you can't really get a precise answer. So we're using this ordering constant in order to rearrange some of the creation and annihilation operators so it's not infinity anymore. Okay, now we talked about closed strings. Closed strings, again, correspond to gravitons, they give rise to the quantized gravity, they just form a loop. Then we have open strings. Open strings give rise to all forces except gravity, and basically all of them give rise to every kind of particle we have. And now let's move to our endpoint, which is interactions of closed and open strings in order to understand theory of everything. So basically unifying all physics. We have a lot of quite difficult approaches to that. Now we're talking about interaction of open strings turning into closed strings. And this is one of the most important theories we have, which is perturbative string theory approach. It looks a bit complicated, but we're not focused on the math part. I'm still going to explain it. The most important variable we have here is A, which is an amplitude. Amplitude tells you the probability of strings interacting. And it's basically the sums of string couplings, and string coupling is the probability of a string splitting. So this is the probability of strings interacting with other strings, and is dependent on the coupling that's only dependent on the string itself, not on the other properties or other strings around it, not on the environment. So we take this string coupling constant and its amplitude for different topologies. So for each topology of a world sheet, again, I'm going to explain, world sheet is a two-dimensional space, and it tells you how the string is moving. And for each topology, for each movement, let's just say of a string propagating in space, oh, it's turned off. It tells you a string coupling and its amplitude, and then we have the amplitude, so the probability of a string interacting with other strings for the whole system. This mathematical part is not as important, but important is that we found that A for open strings is proportional, it's dependent on 1 over k squared, which is just the momentum, plus m squared. But the interesting thing is that we calculated amplitude for open strings, so let's say this type of strings, like the GLA kind of string, and we got the answer that is, it's dependent on m squared, which is for closed strings. So I mean, mathematically, we can say that closed strings properties can emerge from open strings. This is like a mathematical concept, but there is also a theory called boundary state formalism, which tells you why this happens. So it only apparently happens with DRLA kind of strings, so when the ends are attached to the branes. And that the points where the brane is attached to the string, they have fluctuations, quantum fluctuations, and apparently this closed string, they emerge from the quantum fluctuations of the points where open string is tied, let's just say it's fixed to the plane, to the space. The next theory we have is kind of conceptual, it's called open-close connection. So basically when we have an open string, we'll just say this is an open string, and it moves in certain conditions, so it's a Newman kind of open string, it's not attached to branes, some kind of part, it can loop into itself. And this mathematically, it has the same properties as closed string. So that's another kind of interaction when open string can technically become closed string. It can be seen as a closed string. So this is one of the most complicated parts. This is a system of interactions. And this open-closed string field theory, it basically represents theory of everything. So how system of open strings, how system of closed strings, and how system of their interactions, just like the system I told you about, some of the examples, interact with each other. And that gives you the unification of all physics, because again, closed physics is gravitons, quantized gravity. Open strings are all forces except gravity and all particles, and this is the unification of all of those systems. This is pretty much the end of my talk. I hope it was not as complicated, because it was really complicated for me when I was researching all of this stuff. Basically, I tried to explain the concepts, the fundamentals of string theory, just so you have an understanding of how it happened, why is it important, and the most important thing, like my leading point, was what theory of everything is, and that it's not as complicated as we think. Thank you for your attention. Questions, or if I can answer your questions, because some of the things are very complicated, but but yeah, I'm sorry.
Why do the vibrations appear directly in the formula for the string's position?
Why do vibrations what?
Formula.
And the movement formula. That's a very good point. I told you about it, but you might not have heard. So it consists of two parts. One part is basically like a static line between the points of string points, and one part is it's the sum of vibrations. I had a separate slide for this vibrations. So basically, it tells you the position of a point, but the oscillation is important because why? Because string is a wave. And its oscillation, its vibration, it's directly proportional. It tells you where the particle is. So if you only have a static line, it won't work because string is not like this. String is a wave. Yes?
You mentioned in one of the formulas that string itself was split.
That was split?
The string.
Yes.
Yeah. Why would you split? Like, how would you split? What would that be?
That's just what topologically happens to a string. It's like a mathematical formula, so it was not necessary for my paper to include it. That's why I didn't include it.
Open string split into closed string and open, or like something like that, like in the interaction term, right?
Yes, in the interaction terms.
Another question. When you were talking earlier about how the open strings can loop around and behave like closed strings, does that mean that like a photon or something can start behaving like a graviton? Or is that hinting that they have some kind of gravity?
That's a good question. I told you about the experiment in hadrons, that actually a particle can emerge, for example, from the interaction, because the excitation level I told you about, it changes with the vibration of strings. So, for example, you add some power, the vibrational mode of a string changes, and you have a different particle. So the answer to that is yes, and the particle does not really depend on the, let's just say, not only the geometry of a string, but also it's mainly the vibration of a string. So if something happens to an open string, it might still be the same particle. Because geometrically, for example, it's split, or something happened to it, but the vibration level stays the same. So the mass and, like, for example, the spin of a particle is the same.
I have a question. When you showed the mass, was it a gravitational mass?
No, it's mass of the particle.
Mass, but it's a, because I remember in physics there was some investigation to distinguish between gravitational mass and inertial mass.
Yes.
Yes. So this is the gravitational mass, probably.
Yes. Then yeah.
Okay, but it's represented now as an operator. Okay. So as it's an operator, it can have a spectrum. So does it mean that this mass can have different values, different eigenvalues? So, your question?
No, I was going to talk about. Well, never mind. No, it's okay.
So I mean, this is an operator because usually we have just a particle has a mass, and never we observe that the same particle, like by some jump, has another mass. So does it mean that this operator has just one eigenvalue, so only one possible value?
Only one possible value for the properties of a string, you're telling me?
No, I mean, for this, you have this m squared equals 2, then the operator of the number of particles, number of smalls, minus creation operator, yes?
Yes.
So this expression is an operator, yes?
Yes.
So it's an operator, it has eigenvalues. And if it has more than one, then in principle we should observe that the mass just changes to another value. Do you understand? So
This operator is defined by a shifted number operator, and number operators work on defined like stationary states of, if you're acting on some kind of like wave function or whatever, like you're taking this operator and applying it to some state. At least in my interpretation, it looks like it's a shifted number operator, which is essentially an identity operator for whatever your state is. So I think it will give one well-defined value of mass. Yeah, dependent on your state's topology.
Okay, I guess that's it. Thanks for your time.
Okay, so everyone, hope you like the talk of Natia. Please, a round of applause again for her, please. So I think you're all waiting for it. We'll have around 20 minutes break, 15 minutes break for so you can eat pizza. After this break, we'll start our second talk about how to optimize irrigation in Tukala, given by Zakaria Ghuddan. Thank you very much.
Now I'm it's very interesting though. I did not get most of it. I mean, what is interesting though is like is the idea that basically so basically there's not as many right now. Maybe when it is proven. Physics. That's like in IB we have standard levels.
This morning.
So the standard level.
Passing by the window, I saw you. I watched you and Medley.
It's not. I'm just gonna go for dinner. I've had this straight from 2 o'clock. Thanks for letting enjoy your game. Last question and yes, Northcap is every Tuesday, right?
Every Tuesday, yeah. I did a bit of math.
Are you attending the consulting one, the UCG?
Well, I think I signed up for it, but because I don't have
It's a Monday. Oh, not trying to set. I could never bring myself to do that. Too sad.
Alright, see you.
I reached Asgor's house, right? And I saw like it's an identical replica of Toriel's house in the ruins. But like some slight changes like that, gifts and all, like bro, it was so sad, And then I had to kill him, and then I had to kill Flowey, and now I'm gonna go back and get the true pacifist truth and explore the true lab next week.
Not repeat it again.
Let's see why this is popular.
I have not played games in a while. I saw the mock version of this.
God told me.
Mahdi didn't want me to be there.
Yeah. And then I told me he didn't want anyone to be there, like only him.
But they invited me.
They invited you, and then he said no.
No, they invited me. I was there, and then they were like, "No, leave." And I was like, "Bro, what? Like, I cleared my schedule to come here, bro. Like, what do you mean?"
Crazy.
Just don't tell them because they're gonna be like disappointed.
Why?
No, like, bro, they're just gonna think I came to see Noah, and then I left.
I was talking with Dana, and I don't see why you should be like alone. You know, like just one person. The more people who see it, the more people can get feedback, right? Yeah. The better it can be. It'll be more realistic to this.
I'm not gonna tell him to leave, and he goes to the And I was like, bro, I was actually mad. Because I was like, bro, come on. I want to learn math. Like, after I just went back, and I just told them, Magri wants me to leave. And I put Magri on the awkward spot. He was like, there, bro.
He did. You're fine. Reasoning.
I don't know, but it was fine in the end.
Еще у вас есть
What was your last one?
I don't know. But once I was there, when they performed, they were like, no, we want to hear your opinion. And I was like, yeah.
He was wrong.
No, that's fine. That's fine. That's fine.
Besides Zakaria is a goat.
Where's the career?
Это что?
No, I get a feeling that mini golf is one of those.
I suck at it, bro. After, you know how we went after? I lost by like 11 points, dude.
Was that your brother?
The long hair? Yeah. Right. He wants to do like more engineering stuff, not
That's so cool, actually. Both physicists.
some sense, yeah.
It's so cool, actually.
Pretty much, exactly.
Yeah, you guys are gonna conquer the world. Did they just happen to be here, or did your parents?
No, they plan to visit, yeah.
His talk was pretty good. I'm
Well, that was like not my talk, bro. Yeah, no. That was just me whiteboard yapping. Like we didn't get to use the slides. I just raw dogged the presentation on a whiteboard.
You know everything.
Yeah. Well, sure. You know, it made me change my topic like a couple times. I was originally gonna do it on like Möbius map and the chaotic dynamics, but they didn't like.
Why didn't they like it?
Because I already knew it. No.
Oh, that when you apply it, it's just another Mobius.
So there's this map. It's like ax plus b over cx plus d. That's the map. And what happens when you iterate it is
Just another Mobius.
no. It gives you like so if you treated it like a matrix a b c d and you squared it, the coefficients in each would be exactly what the coefficient. And that's why it's cool. And so any like matrix dynamics you want, you can model as a function instead.
I remember Arna was.
Try it out. Try it.
Yeah, we tried it. Factor it out.
It's like nice. Yeah.
Sweet. Arna, it's like. First important to everyone. Started teaching me bifurcation. All the time. It's fun. Fun. Yeah, it was like. Arna's behavior. Just like second TA session, he was like, "You need to know what the Cantor set is."
He loves his Cantor set.
Should have been here 30 minutes ago.
It's like this set that.
Real now.
Change the color of
Objective special set.
I'll just get over it.
G is actually the easiest. I have.
just out of interest, Professor.
It's not the Eric.
Everything's fine, but you know, future to any school have this professors like CS50 course at Harvard. No, it's like introduction to computer science from Harvard University. It's probably interesting.
I love your experience. That was my your first year?
Half Russian, so I'm half Russian. I'm still confused about gender and me.
Well,
I want to be years. The thing about EC though is that like I'm caught up with GE right now so much that I'm behind other subjects, and when I try to the level up, I'm behind PE.
how do you find physics though?
Physics, matrix algebra. What's wrong with I do a random sport cannot skip this class because he explains like 2 years of material. we went getting started explaining derivatives, like in this lecture or something, the homework was diabolical. I was learning calculus for like 2 years and it was even and today we also just like for the trial. Today we also explained some derivative stuff like graphics, and then he said next time we're going to do integration, and it took me like 6 months to like. It's crazy. It's crazy.
Algebra and calculus in one course.
You have applied, right?
I have applied elements.
Yeah, that's my team. So,
Learn the practical.
that's how university works.
Yeah, well, I mean, you don't expect practical lectures.
No, I really love it. It really is my passion. It's just
There are other subjects.
if you're
I think I've already have a degree in like second bachelor's already. University's like still.
I really want to stabilize my life.
It's not struggle, it just takes time. It's not struggle. I wouldn't say that I struggle, it just takes time. And it should take time.
Knowing how bad
With the time to enjoy this, pressure, I
that's sad. That's so sad. I love it. Second family.
third year when you're done, you're going to be taught to stress.
They taught me.
That skill that you develop being numb to stress is
Character development, right?
We studied there, we spent time in China, like
science is very complicated. Majority of them engineers.
you know what, we can't sleep.
And the electrical engineers, so
Good for us.
yeah.
Starting?
This one I just. Come into MFCS tutorial. I tried. I really tried.
How hard? You must think language learning.
This week is very tough.
You just
I mean, in MFCS or you mean in like
No, I mean,
equation.
hard. Definitely. No, if you're fine or you're not fine, you're not. Linear algebra was super hard. I think more than always. Seriously.
Matrix algebra. Systems solves that.
linear algebra? No. Yes, it's called elements, and the one is called linear algebra.
I took it.
Half of the
It's made but OS, it's not the same. You algebra, if you work with it, I'm getting more comfortable. OS,
apparently historians like
linear algebra, but
for it, like
linear algebra in your
Linear algebra. I'm dead. I'm dead.
Oh, yeah, but it's hard, but like if you work with it,
Your experience, my guy. I'm not.
no, actually, the only time I didn't take in high school was linear algebra. Like, to be precise, so in my grade, in my generation basically, I've had protests more of like, some professors didn't teach.
it's like paper.
And because of that, like the government like changed the program just for our specific
Against
differential equations for mathematics.
Okay, so
Our generation basically, you know. And one of the things that got removed from math sciences was the linear algebra.
I think maybe not the same, but you know what? It's interesting because in my country, I don't know what's now. My brother studies at school. Have to ask him. But we didn't have derivatives. We didn't have integrals. We didn't have vectors in mathematics. It was terrible.
That's so much, you know.
It was terrible. And, but my dad was back in Soviet. He had all of this. He had no limits. So
Like Morocco, so math science is pretty crazy. If you look at math science before, like this generation, they just program like 90. Each professor of math, you know, before, oh, they didn't work before. Bro, they had abstract algebra in 8th grade. They had number theory in 7th grade.
yes,
You realize at 11 years old, it's already like homomorphism. When you're going to do abstract algebra, you find yourself that you had this in Morocco in 8th grade.
and that's great. Yeah.
I had it now in Morocco. The only people that have it is the actual graders, math sciences, you know, like the things that I choose to do.
Yeah.
If you're not math sciences, then you don't do it.
Yeah, that's why you guys become TAs at MFCS. Yeah, that's good.
Right. it of course helps. Like,
It helps.
it helps a lot. Like, I'm trying to say, like, it didn't help me. It of course helped me. But it's not like the thing that's gonna make you. I mean, it makes it easier, but not easy. You know, you still have to do it. Like, I didn't have Boolean algebra, graph theory, many things, relations. I didn't have. So of course it helps.
An hour and a half, definitely.
But listen, about linear algebra, even the genius told me that it wasn't hard for him. If it was hard for him, that is really hard.
No, it doesn't mean anything. A lot of hard work they have to put in.
No, I mean, but you still have to like what you're doing. I mean, did you like? Because Pablo told me that it was very not very theoretical.
Yeah, a lot. I know. Me with like n dimensions, 20 dimensions, 30 dimensions.
Yes.
But it's the thing. I'm like, now I know linear algebra. People take to think about it.
Are you taking elements of linear algebra?
No. I can't be TA like if you think that you didn't teach, that you didn't have. I took matrix algebra in the last class last year. Yeah. Like now, when I'm done with, I'm like now I know linear algebra. Like more like it's just yourself.
Okay, 7 in the middle.
If you put work on it,
You have left your rest.
to be honest with you, like 91 linear algebra. We're done, I go to 95. And we're not math majors, If you put work, I know she worked on it.
I can imagine.
When you work on it, you can do it.
But did you like it so much? The course itself?
At the beginning, I really hated it. At the beginning, I was like, what the fuck is this, But like, I know it's useful for, it's useful for but she already this is what I'm
It's linear algebra. Yeah.
So it's, you're gonna regret it, Will you like it? I don't know. Do you like FCS?
Well, actually, I would say the first courses when they were I was a bit, but now when we had algorithms, when we have linear algebra, when we have +1 operations, I liked it a lot. This one was much better.
You want a minute?
Yes.
What do you mean 1 minute?
And he just uploaded like one.
It'll be 15 minutes.
I'll say it like this. We start in a few minutes. 1 minute.
Like, what's your gut analysis?
The chain,
Like, how?
My third one.
Like, you were like
no,
20. Like, what, like,
what I wanted to say. Yeah, I feel like you're doing this all the time. It's fucking good.
Guys, thank you. We'll start in a few minutes. Zacharias talk. So just be ready, please. Thank you very much. موجود. لا تشجيع اخي شوف ثقة في النفس ان شاء الله يكون خير. شو المغاربة كاملين؟ خلينا مرة جاية. كويس رئيس بيتي. شو سميت الصوت ديالك كامل؟
Optimism and wrong usage. Optimism and wrong usage.
No, ولا I don't. Bathroom just here. You can run. We're gonna start now. Optimizing drone irrigation.
Optimizing irrigation and wrong usage.
Optimizing irrigation and drone usage.
Immigration?
Irrigation, not immigration. Like enter and the others don't. Bro, what the?
Bro is gonna get the book.
I stole his seat.
It's easy to understand.
I am doing the 100. I'll get probably.
No, you shouldn't have let go. You shouldn't have let it go.
You wrote 100 in the first
Dana.
Yes.
Okay. Guys, please can you take seats?
That's so smooth.
I got like one.
So بروج لا عليك سيف جلس في كرسي كرسي خير. So hope you're all ready, because now we'll start the second talk of this third edition of the undergraduate seminar, namely called Optimizing the Irrigation and Drone Usage, and specifically in Dukkala by Zakaria Ghuddan. Please welcome Zakaria.
Hello everyone. First of all, thanks for coming, and I want to say a special thanks to all the guys, Ahmed, Loredan, and also the guys presenting, and also a special thanks to my father, who helped me a lot in the agronomical part. So, as Ahmed said, today I will be presenting the optimizing irrigation and drone motion in the Dukkala region in Morocco. So, as you know, as an agronomer, we have to worry about how could we manage our field and our outcome. And hiring agronomers and topographers is going to be way above their limits. So this is when comes a new way to maybe reduce the budget of the agronomers. And I will be dividing my talk into two parts. So I'm going to take the Dukkala region as an example here. So basically, it's a field in Morocco which is the most, which has the most outcome in Morocco, and just to explain how the stress is like it's a semi-arid place and it has irregular rainfall and high evapotranspiration. So here the integration solution, we have the mathematical model of water demand, hydraulic flow and energy, and UAV imaging, and centimetrical resolution of subfield variability, and optimizing the variable rate irrigation and vehicle routing. Okay, so as I said, I will present a blank page. So drones are not specifically made for this task. So we have to implement them with plenty of new relations. And I will be dividing my work into two types of relations, the agronomic relations and the technological relations. So starting with the first relation, which is crop evapotranspiration. So it's a composed word, as you can see, it's evaporation and transpiration. And actually the usage of it is to see how the field reacts to the water usage, how it transpires. It's a human body, and how how the water actually evaporates. So we're using this formula. We're going to define ETC as the actual crop evapotranspiration, what we are seeking to know. ET0 as the reference evapotranspiration, and QC as the crop coefficient. As you can see, we can define. We have the definitions ahead of us, like evapotranspiration. We already talked about it. EC is the factor reflection, canopy density, height, albedo phenology. So this basically just depends on the land. And H0, the demand for short grass reference surface. So this is basically the demand of the water. So as I said, we just took an example here, and after computing, it gives us 6.9. Let's just remember the values because we're going to use it at the end. So for the second relation, it depends on how the weather is. Because if we don't have rain, we won't be using it because IN is going to be equal to ETC. Because the other components are dependent on water. And if there is no rain, there is no water. So there won't be any point of using this irrigation. But in this case, we'll just pretend that we have rainfall. So we'll be defining IN as the net irrigation depth needed. So this is the water requirement. P as the effective rainfall, so how many rain we had that day. And delta S as the soil water storage change, so how the field actually stores the water. So, of course, water is a key element in our work, and we have to keep a flow ongoing. And for that, the Hazen-Williams relation comes in, where we define Q as the discharge, C as roughness, D as the internal pipe diameter, and S as the head loss gradient. So basically, we are using this formula to have a quick design of the material and the design we're going to have in the pipes. So we actually have enough water demand, so we don't have an overflow or a need in the water. So after computing this Hazen-Williams relation, we have 30.5 liters per second. So this is the basic need, the basic water flow we have to keep. If we exceed it, we are going to have a water flow. If we have less, we are having let's say, an underflow, I guess. So, of course, to pump this water, we are going to need power. So this is when the pump power relation comes in, where we define P as the pump shaft power. So this is the pump that actually pushes the power. Rho as the density, G as the gravity, Q as the flow rate, and H as the total dynamic head. So it's statics, friction, and pressure. And we're taking nu as the pump efficiency. It usually ranges between 0.6 and 0.75. This just depends on the pump, so we can't really define it at the moment. And as I said, the use of it is to actually have a comparison of the layout via impact on H, which is as I said, the dynamic head. So it really depends on the static, friction, and pressure, as I said. So after computation, we have 6.8 kilowatts. We actually measure it to 7 kilowatts because actually the pump only takes these kind of numbers. So this is a basic illustration of how the pump works. So usually the pump is here. I don't know why this happened. It just goes and distributes the water in the field. As I said, it's a 12-hectare field, so it's pretty big. So it just goes on and it distributes equally for the field needs. So moving on to the period and water volume. So actually the use of it is to convert daily depth to monthly volume for energy and cost planning. So the talk actually gets kind of economical in this part, and also we will get to it during the talk. So we'll define here W as the monthly water depth, IN as the net irrigation requirements for the field, and V as the monthly volume of the area we are doing the work on. And so after computation, we have IN that we computed at the first, it's 6.9 millimeters a day, W 107 millimeters, H 12 hectares. So it computes to V equals 24,840 cube meters. So it's a very large number, noting that the field is 12 hectares. So it usually just depends on how field is in width and yeah. So now moving into the technological mathematics. So starting with the ground sampling distance. So the use of this relation is to actually set an altitude to reach the target spatial resolution for agronomic indices. So we're using this formula so that the drone can actually differentiate different areas of the field. And we'll be defining GSD as the ground size pixel. So each pixel for every ground size, H as the altitude, and SP as the sensor pixel pitch, and F as the focal length. So after computation, it gives us 0.03 meters per pixel, which is 3 centimeters per pixel. So this is the maximum efficiency of the drone in the given altitude. So going on to the effective swap with overlap. So this actually defines the line spacing to ensure complete coverage and good mosaicing. So this ensures that the whole field is scanned and there is no dead zones that weren't reachable by the drone. So we are defining the EFF as the usable swath between flight lines, and WF as the raw footprint, and phi to y as the lateral overlap ratio. So after computation, we have 36 meters. This actually goes by. So between each flight, there will be 36 meters. 36 meters, the drone goes down. 36 meters, the drone goes down until the area is fully scanned. Of course, endurance and coverage are very important and essential elements for this because it varies to each drone, but we'll just take an example of the latest drone that are on the market. So, as I said, it estimates the sources for field image, rate, speed, overlap, and time. So this estimates how much time it's going to take to actually do all the previous work we were talking about. So here is a flight path diagram. So the drone usually starts from here. It goes all the way to the end, comes back, and goes until it scans the whole field. So now, moving on to a kind of a mix of the agronomical and the technological formulas. We have the NDVI, which is the repartition zones for VRI. So this basically divides the zones concerning the needs. For example, if it's stressed, it's moderate, or if it is in a good shape. So this is a very basic formula. We are defining NIR as the near infrared reflectance and R as the red band reflectance. So it's just some kind of reflex that makes the work easier for us. So here is an NDVI interpretation scale. So this is what the agronomer has. If the NDVI ranges is less than 0.2, so the vegetation is stressed. So it gives us a red sign. If it ranges between 0.2 and 0.5, it's moderate. It's just a yellow Q. And if it's above 0.5, it's a healthy green Q. So this is basically the image we have. As I said, it's still the field in the color. As we can say, it's very well-rounded, I'd say. And this actually is going to help us in the next steps because it's going to, I think it's, yeah, it's here. It's going to give us each need for every part because it's going to vary. We can choose the same thing in different parts. So going on to the irrigation allocation. So basically, it's allocate limited water among NDVI zones to maximize profits. So this is what I was saying. It makes the agronomer pay less and actually to have a better outcome. We are going to be defining WZ as the water depth in zone, P as the price, cube meter as the water cost, Y as the yield response, and WTOT as the total available water. So these are inputs that the agronomer has to put, so we can't just give random values because it won't make sense. So moving on to the next relationship is the yield water response. So this is basically how the yield response to this is basically how the yield response to the water given. We are defining Y as the yield at depth, Y max as the potential yield, and K as the steepness, and W0 as threshold before quick response. So it just captures, so the usage just captures dimension returns, supports the efficient irrigation. So going on to the drone routing, this is where we are going to actually input new relations to the software of the drone. So basically this drone routing, we use it to have a minimal total time between distances and have an energy for full coverage under battery constraints. so that the drones don't stop working mid work, so that it's basically just for us to save time, energy, and also money for the agronomers. So basically, we are setting waypoints for the drones to have to use. So it goes from I to G, I to G, I to G, I to G, because it has a binary route going from 0, 1, 0, 1, 0, 1, and it goes on. So this is we made it into an algorithm. We are inputting the waypoint set V and the cost matrix CIG and the endurance Tmax. We are inputting to analyze and visit node lists. So the node list that the drone couldn't make sure, and for each drone KD. So for each drone to go to the KIG. So are starting from the depot, while the remaining endurance is above 0, so it doesn't the drone doesn't stop mid-air. And unvisited nodes exist too. We choose the nearest unvisited node with feasible returns, so IG again, and add node to route, updated time and endurance, and while and for, and we have an output routes for all drones, so they don't collide and they do all the work. So finally, we're having a case study of the Ducala wheat field. We will be inputting all our relations. So to put us in context, we have a 12-hectare parcel near Sidi Ben Noor, a clay loam soil, pressurized PVC network with electric pump. We have the parameters here. We have the daily temperature, which is 25 degrees, solar radiation 22, wind speed 2.5, relative humidity 55, so it's pretty much humid. We have a reference ET0 6.0 millimeters a day. We have crop efficiency QC1 1.15. So we are using a water requirement and energy costs, which is the latest formulas, and also the first formulas that we had about ETC, the evapotranspiration. As I said, we are not using the second formula because we don't have a rainy day. And after computation, we assume that the energy cost is 1.5 dirhams per kilowatt, and pump power is 6.8 kilowatts with 48 cubic meters each pump rate. So E equals to 6.8 times 24,840 divided by 48, which gives us 3,517 kilowatts per yes. So the basic cost for this is 4,220 dirhams a month, which is approximately 400 euros a month. So I have a drone operating plan and route figures. So just an example of how the drone does the flight paths in the 12-hectare field. And we'll just have a discussion about the economical part and the water use efficiency. So as we said, we have already set the monthly demand. We assume that the 10% loss is effective. We have the pumping at 0.17 dirhams per cubic meters, and it equals to 480 dirhams a month in energy savings. So as I said, it's the yield gain and financial return. This is what's the outcome of the field. It's 6 tons, and the additional revenue for the agronomers, it's approximately 1,800 euros. So the net income is approximately 105,000 euros. So it's not really that important to know, but it's a case study. So this is just an analysis concept of how the relative yield responds to the water supplies. We can see that it's going up and then getting static. So this is just an interpretation for non-engineers. So this is what actually the agronomers should know: how to optimize water productivity, not only absolute yield, equalize marginal value of water access in DVI zones, data-driven targeting, less waste, more profit, and sustainability. So we have the outline conclusions. So we have a precise daily demand, hydraulics, and power quantify feasibility per cost. UAV and NDVI turns images into irrigation set points via VRA. VRP, operational efficiency, coverage, under endurance. So for future work, we have real-time sensors, ML stress prediction, and weather coupling. So just some basic computation of the path relations. That is just a algorithmic way, and they're just going on with the elements, and that's basically it. So thank you very much for your time. So any questions? Sure.
This was one of the most practical talks I've ever heard. It's actually very, very on point with like how to do the things. Okay. And I wanted to know, is this already implemented in Wada?
No, it's not.
This is a proposal you're gonna
Yeah,
make.
it's still not an approved project. There is no concrete no concrete papers or official sources that claims that it is approved by. So in Morocco we have the Ministry of Agronomy. It still didn't implement any new technologies. So this is not a thing that they would think about at the moment. So yeah,
Prove it.
prove it.
Soon.
Yeah.
Sure.
When you talk about classifying each of your unit cells, like in your grid, you say green, yellow, or red, right? And you do it based on the reflectance.
Yeah.
Is the reason that we use red band reflectance just because, like, when we look at the crops and they're more yellow,
Yeah.
like that's how we gauge it by the color of the crop, or
No. It's actually
reflectance?
actually the let me just go to the. So here, this is what you're talking about.
A little before the algorithm for it with the reflectance. Yeah, this one.
Okay, so basically, when the drone flies, the sensor actually sends UV lights, and it's reflective. And when it reflects, it gives us the infrared reflectance and the red band reflectance, which are the two components of our relation. So when it does that, the outcome of it just gives us the stress vegetation models are healthy, and as an outcome of it, so it's more practical for the farmers. It just gives him a table like this where you have the stressed part, the moderate part, and the
So, yeah,
other
yeah.
part.
So based on the biological condition of the plant, the light that's reflected has different spectra?
Yeah, that's exactly. So
I have a question about the time of the day in which this water is applied, because I think when the sun is very strong, if you apply the water, then it will be vaporized. So do you apply water in some like morning, evening?
Basically, as I said, we have two formulas at first, which actually gives us how the water is evaporating during the day, and the second relation is when there is rain. So as you said, there is a difference if the sun is way hotter than usual or there is more rain. We don't have a static value. So based on the day, we input we input the components, and based on the outcome, we define how is the field doing that day. If it's evaporating more water, or if it's storing more water. So this is actually the starting point of our work.
amazing example of how math is used in real life. And next we are going to move to Noah's talk, but we have a 5 minutes break in between.
I probably forgot most of it.
Я подумал, что ты сказал, что
Dude, I made it like from last talk. I saw last talk as well.
спасибо, да. Ну, оно вроде как правильно все. Я себя чувствую прям.
Yeah.
Ну, не нагружать, то есть не начинать. Я вообще без костылей лучше не приберечь, а потом еще на неделе все равно. Потом
Yeah.
See the fluorine shows more fluorine. You know what?
this one's the most
It shows understand like more picture. These pictures, yeah.
Like it's very clear.
Like, you know, I searched for
кто-то изучает сами.
picture.
I mean, it's just calculate Lagrangian, solve the equation. Plain. The equation is right.
But it's good though. Yeah, it's good.
Drop some variational calculus.
No, I'm kidding.
You know it, right?
Yeah, what's up, drop?
Nice to meet you.
Me too.
That's third year, right? You're about to finish it. Physics.
Yeah.
What are you going to specialize in?
What am I gonna talk? Or
No,
what?
I mean,
like in general.
Career, yeah.
I want to become a theoretical physicist as like a consultant.
So you want to teach, basically.
Teaching or work in computational modeling for nuclear fusion. Nuclear fusion is my interest, plasma physics specifically, and magnetohydrodynamics. Yeah, talk is different.
Yeah. It's just interesting to talk.
Yeah, of course.
And how you came up with it. You have some
Well, in school, no. I wanted to be a filmmaker up until 12th grade. Like, I applied to film school, and halfway through my application process, I'm like, actually, I want to become a theoretical physicist. I switched very drastically, and I'm very glad I did. I think this line of work will be much more fulfilling. I've learned it all from the last 3 years. Yes.
mathematicians?
Oh, no, not at all. My father has a doctorate in education, like just so he works at education administration.
Okay.
So I've moved around a lot. Like he works at international schools. So I move countries a lot, but no.
Where are you from?
USA originally. Yeah, but I've lived most of my life, maybe 13 years outside of the US. Just every 4 years I move different countries. So Colombia, Bulgaria, Germany, Hawaii, yeah, many places.
Very good.
And you?
I'm from Belarus and I'm CS. So it's just very interesting. I talked to math majors and physics majors.
Yeah.
It's very interesting to understand how people develop that. Like, yeah,
I think it's very interesting. Yeah. I think it'll be fun. Very rewarding. If anything, also I very much like teaching. Professor would also work.
No, with your computational mindset, you will be successful everywhere.
Both. We'll see.
It's very good. I mean, I talked to that there are a lot of businessmen or the CEO
That need the yeah.
and then are like physicists. Okay, my dad is an electrical engineer. He doesn't work a day in it, right? But it helps a lot.
Yeah.
And with your physics, it's just it's hard for that.
They're true. Like they're very good with financial modeling, and like sometimes they will hire them over economics.
Over economics.
Yeah, because they know how to actually model and do stuff like this. Make decisions and things like that. I'm doing it for fun. They asked me to make a talk. I hope it'll be interesting. It's lighthearted. It's about mini golf. Yeah, how to model it though, mathematically perfect. For any golf course. So basically for any golf course and for any shot,
Golf like
for any golf course, any shot that you make, exactly how to simulate it, model it, yeah. Analytically.
And did you know about it
North America.
when you researched the idea, or did you know about it?
I just had I played mini golf one day and I'm like, okay, this could be fun.
Oh.
So no, I think no, the actual like mathematics maybe it's not so advanced. I think you'll be able to follow. Thank you. Enjoy. Set up presentation, brother. This week, orange.
I think this is pretty fair.
The thing is, my thing's on a green background, so I shouldn't be using it. Yeah, white. Oh, that's not white. It's if you use the other side. You thicker, I think, right?
Where's my mouse?
Left up.
You started.
Oh, are you ready?
I'm ready, let's go.
We start now.
Show me this.
Do you want to make the intro?
So it's like Lagrangian push-put. So what's the title like you?
How to play mini golf. How to predict mini golf shots.
Okay.
It's not that deep. It's 13.
I said Lagrangian push-put, you know?
Sure, Lagrangian.
But you know what his research about? Do you know what his research about? So Lagrangian push-put.
Research is.
But you said it's a new thing.
Lagrangian push-put.
What's that? The question is new.
So Lagrangian push-put.
I just applied my knowledge.
It's mini golf.
Ah.
Basic research. No, like research. I go too much more.
If you wanted to write before,
It's about iterative, like chaotic dynamics of Möbius maps, and I think that would be too much. You remember that matrix thing I talked about?
yeah, that's the thing.
How you can.
Be grateful that I came, and I'm grateful that
Yeah.
And how a consecutive application of this is. Yeah. And how you can use this to get out the golden ratio and model infinite resistor networks.
I think mini golf is more interesting. I think mini golf is more interesting.
This guy. Specifically, but if this is represented with the Möbius map and you evaluate it, it gives you 5. It gives you the golden ratio.
Może jest fotografii.
That's not what I'm talking about.
Okay, everyone. I don't know how to do this.
Are you already preparing that?
Wait, I didn't open your slide. I didn't open your slide.
Tell them to sit. Okay.
I mean, just open his slides first.
Yeah. Oh, I need my little slide.
Where are you going?
yes, let's go and rest. Tomorrow I have 6 classes. Something acceptable.
So guys, can you please take seats? تفكر بالسكتيلية بالسكتيلية. So hope you're ready for our last talk. I mean, how do we say it? Last but not least, last talk, Lagrangian mini golf and Lagrangian put. Thank you very much. No, thank you very much.
So for this talk, I wanted to do something fun where I bridge physics and mathematics as closely as I can while introducing some interesting concepts in calculus, differential geometry, and just vector algebra. So the idea is sort of to just play around with these tools and see what kind of cool things we can model. In this case, mathematically perfect mini golf. That's the goal. Let's see if it works. Cool. So I'm just going to go through it basically, and we're going to sort of go constructing our model piece by piece to sort of eventually get the emergent behavior of what we would consider close to mini golf. And we're going to do it in sort of steps. We're going to first look at how to model a golf ball and how we can represent this mathematically. Then look for a mathematical representation of the course, like what a golf course looks like in the maths world. And then a way to sort of combine them together and extract some meaningful dynamics by applying physics. So first we develop our model with mathematics and then apply real world theory and physics to sort of squish these two together and get something meaningful out of it. That's the idea. To start, we're going to figure out how we can represent a golf ball. In my case, I'm looking at a very simplified model. We treat the golf ball as a point particle, just a single point, and we sort of think, okay, what is a golf ball? What is a golf ball? What do we need to describe it? And it really comes down to, if you want at its simplest, it is just a point in space, represented by 3 coordinates, x, y, and z. So really a golf ball, in its unconstrained form, has 3 degrees of freedom. And as it travels through the golf course, it goes along some trajectory, dependent on the course geometry. Notice it can come off of the page too. There are 3 degrees of freedom at the moment. And this is really all you need to describe a golf ball. Notice here I've defined it also with some time parameter, which means that over time this position can change. That way we have this generalization. And if we know a golf ball's trajectory, then from physics we know that anything that moves and has a mass, m, also has its energies. So it has kinetic energy and also a potential energy. The kinetic energy is just defined as, half mv squared. The time derivative of position is velocity, as we know. And we denote it simply with a little dot on top. So whenever you see a dot on top, that just means I'm looking at the velocity or the rate of change of that coordinate. In my model, gravity does exist. I'm not negating that much. I will negate friction, but gravity exists, so it has potential energy too. So this is an example of a golf course. We have our golf ball, we make our shot, and the trajectory and its position flows with a time parameter, like so. This, in a sense, a golf course can be represented then as a 2-dimensional surface, so sort of with 2 parameters in 3D. So really the course is represented as the third spatial component, the height, is equal to a function of the x and y coordinates. This is how we define our surface. I further required in the paper rigorously to be twice continuously differentiable, but this is because we need some kind of description of the curvature to look at it meaningfully. Okay, so now that we have this arbitrary golf ball and we have this course, we want to find some way to marry these two together. We want to connect them. So the idea is I introduce what I call a holonomic constraint. In Lagrangian mechanics and in mechanics in general, a holonomic constraint is any constraint which is completely independent of time. So only dependent on our Q1 and Q2 in this case. And the constraint I want to say is if we have some surface that the golf ball is, lives on, then it is stuck to that surface. And the way that I write that is then that its third component, wherever its Q1 and Q2 is, its height has to be stuck to the course. So that's how I stick them together. And with this constraint now realize we lose 1 degree of freedom. We go from having 3 to now having 2 because the third component is completely described by Q1 and Q2. So with this we have simplified our model in a sense, even though we're introducing more complicated behavior, which is kind of nice. Now we only need 2 coordinates to describe it, both of which are dependent on 1, which is time. So, when constrained, velocity is no longer written with x, y, and z, or q1, q2, q3. It's written now simply as q1, q2, and then the time derivative of whatever this height position is dependent. From a lot of you who have taken multivariable calculus know that we should apply chain rule here. we have this time parameter and two time-dependent components. So of course, we expand it as usual, like this, okay? So what a partial derivative here means is sort of how much this slope changes with respect to it's moving back and forth, and this would be moving on the Q2 axis. So how much we go up and down based on moving locally a small amount in Q2. And when we multiply it by the velocity, we are getting the vertical velocity there. So that's the idea. Expanding this all out and plugging it into our kinetic energy, we now have an expression of the kinetic energy only in terms of Q1 and Q2. And of course our height field. So that's nice. And then EP, instead of having Q3 here, we write it as H. Because, yeah, okay. That makes sense. Now, we have this very complicated expression for the kinetic energy. It might, it's computable, but it's not really nice when we want to write something very elegantly. So in mathematics, sometimes what we like to do is further abstract our notation and introduce this as some kind of product between vectors and matrices. So the puzzle now is to figure out some matrix that when we multiply the velocity vector on both sides, we get this out. And I've done the work. And if we define a matrix G that's written like this, where these are just the partial derivatives of H with respect to Q1, Q2, we get out this matrix where if I, yeah, sure. Let's go. Yeah, where if I plug this matrix in, my kinetic energy can be written now as this much more simplified expression. So instead of being half mv squared, where my height component is there, it's all encoded in this G. And this G we call a metric. It defines it encodes this third degree of freedom that's hidden from us normally. And now all we need is these two components to still describe the velocity the same way. So that's what a metric does in this case. It sort of encodes our third degree of freedom and how the space varies in a sense that we can describe the kinetic energy more precisely as just a vector. So this is a column vector multiplied by the matrix multiplied by a row vector. So like that. And if we get everything out, it gives us a scalar, which is nice. It gives us a scalar value, so we know that's our kinetic energy. Okay? This is still half mv squared, just now the dot product between these two is defined by this metric. Okay. Now, why have I been looking at these energies all this time? It's because in the real world, things have energy, and we can use that energy to describe the dynamics. And now I'm going to sort of talk a bit about why energy is so important in modeling real-world behavior. In Newtonian mechanics, we sort of try to figure out some system's motion based on the forces that are interacting on this. So the equations of motion now are, we have some mass, there are some forces acting on it, which could be dependent on our degrees of freedom, and we use those to get our descriptions of motion. That is, if we have some point particle, let's say our ball sort of sitting on the golf course, then I would describe this system now as with forces of gravity, the normal force, perhaps friction, and I would take all of these forces and combine them together, and my equations of motion would look like, so we know that the force is equal to ma, or mq double dot, and it would just be the sum over all of these forces. And this would be a second order ODE, and we could solve it. But the thing here, it's a little bit more complicated because as we flow through our golf course and as we move, there are many time-dependent forces, and this equation can become highly nonlinear and not that nice. We want to find some more simplified description that can still give us some kind of nice dynamics. And so what we do is we turn to Lagrangian mechanics, which are a little bit different. So Lagrange looked at a physical system and said, what other ways can I describe motion? And in the real world, when we have some object and it follows some trajectory, the difference between kinetic and potential energy, they transfer themselves minimally. That's the idea. So in a physical system, if I drop this, I know that it has some potential energy, zero kinetic. When I drop it, it goes in a straight line to maximally increase its kinetic energy as fast as possible. When I drop it, it does not go up and down and up and down. That's non-physical. So this term has to be minimized, in a sense, over the trajectory. And if you go more mathematically, it's the action functional. which is just this sum over the changes in kinetic and potential, and we seek to minimize this in a sense, which just means kinetic and potential energy interchange themselves minimally. Okay, good. And that sort of idea of it changing not so much, we encode into what we call a variational derivative, which we write out for the Lagrangian, which is this difference, as partial L, partial Qi, where this is sort of our ith spatial component, minus d dt, partial L, partial Q dot I. So this is sort of like your rate of change, in a sense, of the differences of your energy. And this should be as minimal as possible, or 0, right? So in real world, this is 0. And everything in the real world sort of will obey this rule, to some extent, if you look big enough. Okay. So we use this equation. We know what the kinetic energy is, we know what the potential energy is, we can compute these partial derivatives, this time derivatives, and get some expression out, which is now our new equations of motion. So instead of doing it with these forces, which is going to be very difficult, we can take our Lagrangian and take the partial derivatives. It describes now the rate of change, and we can do it that way. Get something more physical. Okay, so, yeah, here's sort of what I was saying before. Newtonian mechanics, it's written out sort of like so, but in Lagrangian, it's much more simplified. It's written like so. It works also with any generalized coordinates. Here, we need to use very spatial ones. So this is nicer. We use that, compute the derivatives. We know how to do this. And we get to this big expression here. Okay? Now, just to preserve space and sort of to write this in a more simple way, I have used Einstein's summation notation. And in a lot of sort of more advanced physical subjects, when you have big vectors and sort of matrix valued components, you use this type of notation called Einstein's summation notation to sort of simplify it a lot. Really what you would have here is, since you have this huge dot product between a matrix and a vector, you'd have this huge sum of many products of many terms, but instead we can write it in terms of generalized indices that sort of go up from 1 to 3, or actually even 1 to 2. So when I write out all these k's, i's, and j's, think of this expression now summed over every possible combination of I, j, and k, where they're 1 to 2. Yeah.
No, because here this expression depends on I.
So I is fixed, yeah. And so we have...
So when you have j on bottom and j on top, it's summation and j. But when there is I which is unpaired, it remains.
Yes, so in this case, we would have sort of two different equations, where each one is a sum over j and k, which are pairs which can go from 1 to 2. So it's not so much, but it's nicer to compactify it like this. And doing that, we get this, it's okay, I guess, yeah. Get to this equation, which still sort of look quite large, but it's getting there. And what I found very beautiful about this, and for those who are mathematically inclined, they'll see some very, very interesting result comes out of this. And that is this complicated looking term here, I'll admit, but still central in a lot of what we say in differential geometry. And that is this guy right here, when we treat G as some metric, is a Christoffel symbol. So this right here is a very well-defined notion of the curvature, the local curvature of our Gauss field. And it's cool that it comes out in these equations of motion. That's very nice to see. Recall, like this metric is some first order partial derivative of our height field. And we're taking partial derivatives of that. So we're really kind of looking at the second derivatives of our height field. And if we know from sort of calculus, when we have some height field, the second derivative describes this local sort of concavity and curvature. And so you can kind of think of the Christoffel symbol like a 2D description of this local curvature. And so if you have some golf course, like this, then your Christoffel symbol at different places will sort of look different depending on how much the space is bending in those areas. So right here, we have some consistent curvature here, and it slowly changes to a different type of curvature. And so our Christoffel symbol here will be quite large. Whereas somewhere where the curvature is relatively consistent and our metric doesn't change much, we don't see as much, and so we have a lower Christoffel symbol locally. So notice, yeah, the Christoffel symbol is a function of Q1 and Q2, but it describes our curvature, and that's pretty nice. Now, why is this important? Well, if we rearrange everything and now put it in as our sort of Christoffel symbol, we're almost done, I promise. There's just one more mathematical step we need to do, and that is, it would be nice to get this Q, this acceleration component alone. And right now it's being multiplied by a matrix component. So how do we undo a matrix and get rid of it? We apply inverse, okay? So I denote the inverse with upper indices here. And when I apply this inverse matrix to both sides, this guy drops out. So I'm just left with, well, now Qi, okay, but it should be, Qj. Now this Christoffel symbol becomes a raised one, which I won't explain too in detail, but it just sort of, think of this, but now you also apply the inverse, okay? It's what we call a Christoffel symbol of the second kind. And we just have it here for the other part. And now this is the completely, it's very simple. But remember, of course, there's this hidden sum between j and k. So this is really two equations where we sum over every possible pair of j and k. But these are our equations of motion, which is very nice. And they're really quite interesting. This is what it really looks like if you expand it out. So, very nice. This is why Einstein's summation notation is very good. If we expand this out, we get these, which are a little bit more complicated, right? So that's why I just want to highlight this really nice, convenient way that mathematicians sort of use abstraction to their advantage to effectively communicate. Because we can break down this equation into sort of terms very abstractly. And what I mean by that is, let me rearrange it so we have q dot I equals negative I j k g j. Okay, so now I have sort of the acceleration, and all forces on my object are equal to this guy and this guy. So there's really only two contributions to the acceleration. We can sort of try to think about what these might be. The Christoffel symbol we know is related to the curvature of our surface and the velocity. This term has some velocities in it and the curvature. And so now I want to picture, so what this really means is, okay, pretend you're in a fighter jet, okay? And you're going and going on some flat trajectory and you make a really steep turn up, okay? Your curvature of your trajectory and sort of your flight path, you've changed and you feel a really heavy force down. This force is due to that change in curvature that you have, right? You change from this locally flat curvature to now a more turned one, and so you experience a force. That's what the golf ball feels here. As the golf ball rolls along the field and gets to here, it feels that force, and that's what this guy is. It's a force due to the change in curvature. And now this guy, it's a little more complicated, but it's still some first order expression now of the change in the height field. So we can also think of it sort of maybe as a centrifugal term or some kind of other reaction normal force, okay, that's acting on it. And we can discuss this a little later, but that's sort of, I want to break it down and show that it's not, this is why it's nice to abstract it, because we can break it down into the groups of where the forces really are, instead of looking at this monster. Okay. So take a moment, yeah. Okay. Yeah, okay. So it's good we have a model, but really now it's up to the computationally inclined or just the adventurers to really do something with this. It's very intimidating as it is. So what I've done now is looked at places where we actually solve these equations of motion. The first one, it's a little boring, I admit, but we're going to look at the flat golf course, okay? When we have a flat golf course, we model that with just HQ1, Q2 equals 0. Our height field is 0. And we want to sort of get something out of it. We know G is given like this. So what happens if H is 0? What does this matrix turn into? Identity. The identity matrix, exactly. So we get an identity here. And that means that, yeah, okay, we get an identity, and this is a partial derivative of H, which is also 0. So we have 0 here, and 0 sort of here, okay? Okay? I mean, just trust me, okay? I mean, because we see sort of that we have a... remember, yeah, I guess this term, the Christoffel symbol, is partial derivatives of G, and G is a constant in every entry. So this is 0, and this is 0. And so our equations of motion very nicely, as we would expect, reduce to no horizontal forces acting on our golf ball. If we integrate this 2 times, we know how to do that. We get just the straight line motion. And that's exactly what we observe. So that's good. The model's working so far. Let's step it up a little. Now let's look at some tilted plane. And now I'm stretching the limits of where this can work analytically, okay? But we can still do something analytic with it, which is very powerful. Now we model the height field as some tilted plane, okay? With some value on how much it increases along the Q1 and how much it increases on Q2. The upper indices don't mean squared, that just means the X and Y. I use it just for tensor notation. Okay, now our metric becomes a bunch of constants still. No dependence on Q1, Q2, which is good, okay? And we know that the Christoffel symbol, every term in it is a partial derivative of our entries here. So this also goes to 0. Don't have to do anything with the sums. But this one, we're not as lucky, but we do know that H is first order here, and when doing some expansion, we get out that the acceleration is equal to some constant vector, okay? A, and it's given by this. Okay. If we expand it out, sort of like this, we see that we have so we now see the acceleration on the ball is equal to some constant vector according to the curvature of our surface. So really on our diagram, that would be sort of the acceleration on this point is just consistently pointing down the plane. That's what this guy means. And that's exactly what we would expect. When we integrate it all, we get something quadratic with a forcing term or acceleration down the plane. And so we get this tilted parabola, which is what we would expect. And this is about as much as you can do analytically. Because remember, if not, these become non-zero and you get this monster to deal with. So now I'd like to look at the beauty of numerical methods and why me as a physicist really like to use these numerical methods to do more work on things which would otherwise be an impossible task to take on yourself. Numerical methods are used by physicists as a tool to sort of make a very, very good approximation of the local dynamics and extend it step by step by step by step and take each step well defined to create a whole trajectory, like the one we see here. And playing around with mini golf, I found you can model some pretty diverse systems. Can anyone guess what this system might resemble? The dynamics of? With no friction? If we let the ball sit and sort of swing back and forth. This is a hemisphere. So this is, sorry, I should have specified. This is some hemispherical well. And I've defined, there's an equation for it. But notice, imagine doing the partial derivatives of all of this manually. It would be a nightmare. But with numerical methods, it's a piece of cake. I plug it in and let it work. This is a hemispherical well. That means that according, like from this origin point right here, every place on this surface is fixed. Okay, so there's a fixed length, radius r you could say, or L, to every point here, and we let it swing. And this is exactly modeling a 3D pendulum. So these are the dynamics of a 3D pendulum as a mini golf course, and it really leads to some beautiful patterns. Yeah, okay, so this is one example, but let's go farther. You can also model planetary motion, in a sense. Make your golf course into a potential well. Why not? You have the freedom to do that with numerical methods, which otherwise you wouldn't. You'll see you get this sort of attractor, this fixed point, as it slowly tends down. This geodesic follows a natural curvature. I've terminated it here, but of course you can keep going, and you would see it go spiraling down into this fixed point. And you can do some very interesting things with this. And just any surface you can imagine, numerical methods can now do this in a stable manner, and you get some funky trajectories. And so you can really have fun with mathematics and play with equations that you make. You start with a very simple model, just a vector, with some time parameter. And by applying well-defined physics, you can slowly build up the dynamics to approximate trajectories on any curvature and really have fun with physics and mathematics. So, thank you. Any questions? Yeah.
Did you apply this in real life?
I did apply this in real life. Yes, thank you for asking. And I'm really bad at mini golf. No, I'm kidding. Actually, 2 days ago, I went out to play mini golf. I lost by 11 points.
So the model doesn't quite work without friction.
Yeah, I forgot about friction. If I want to introduce friction, maybe we can talk about it because now it's kind of over. We can do that. Just go back to our equations of motion. And we would add in a term here that's velocity dependent along the curvature, and that would be it, just negative. And there you go. You can put in friction in your model. It's not that bad, because you know friction is tangential to your surface. Take the gradient field, multiply by velocity. So you can put it in. So yeah, but then it becomes not really analytic. So because now you have some non-holonomic constraints. Yeah. Okay. Cool. Yeah. Questions? Yeah.
What is the gamma superindex?
Yeah, so that's actually another one to point out. Gamma, I sort of left it out of this talk, but it's well defined in my paper. This is what we call a Christoffel symbol of the second kind. And you'll see over in the buddy from the other talk, this sort of, it's a very well defined notion in tensor and differential geometry, is raising and lowering indices with a metric. Since G is a metric, we can use it to raise and lower indices. Oh, it's not very nice, is it?
But you have it on another slide.
Yeah, I have it on another slide. Here, so this.
It's totally when you apply on the left.
It sort of eats the eye and turns it in, it raises the eye. That's the idea. It just picks it up. If I applied it again, I'd get more. And sort of this is just a way to represent this application of an inverse matrix. It's very similar. It's just this expression, but now you multiply it by
Like, what object is it? Like, is it like a matrix?
You know, it's well, each component, remember, it's a scalar. Like, this is a scalar, this is a scalar, it's still a scalar. But if you want to take, like, yeah, it's a scalar. And which describes sort of some local curvature along some direction, based on the pairs of whatever your indices are. Yes?
I'm kind of curious on your process of how you discovered these things step by step. Like,
yeah. So, Lagrangian mechanics is a very powerful framework. Like, I think maybe you've gotten the idea. The Lagrangian mechanics you can do a lot with. It's very simple equations, and for any system, if you know the kinetic and potential energy, you can model its dynamics, which makes it amazing. And so, you know, I was out one day on the town playing mini golf, and I thought, okay, how would I make a model of this? And just by making these well-defined assumptions before, the kinetic and potential energy are surprisingly straightforward for something as simple as this, right? And so, yeah, you just sort of apply it to this formula, and if you want to read about how this formula actually comes up more mathematically rigorously, yeah, you can read through it. It's in my paper. But it's the principle of least action, or stationary action, where, like what I was talking about before, objects follow the path of least interchange between kinetic and potential energy. They want to do it as quick as possible and get it over with. Okay. I guess one more thing.
The trajectory of any mechanical system is like a light distribution, so it takes the most optimal path.
Yeah, through energy space, yeah. Really, it's this. So there's some functional, I mean, now if you want, called the action, and it's defined for some trajectory as the integral over your Lagrangian with some, you know, spatial component and some velocities, because this is your difference of kinetic and potential. D, whatever, dt. These are all time dependent on your trajectory. This is precisely sort of just you're summing up every difference term of your potential and kinetic energy. And the idea is you take a derivative of this thing, which has a function argument, but gives out a scalar. These are called functionals, and it leads to this entirely different branch of mathematics called variational calculus, which physicists really like because it describes stuff that's pretty physical, and it comes up in quantum mechanics with your path integral. It comes up with like Lagrangian mechanics, analytical mechanics, and things like that, where we sort of shy away from these forces and sums of big forces and look more at some general quantities which we can write very nicely, like the energies. So, yeah. This is just one playful example of how you can apply it. I guess one more thing to note if you're interested, this equation right here is very shockingly similar to something you see in differential geometry. That is the geodesic equation. If this guy is what takes into account gravity, everything here is your forces due to gravity. If you take away gravity, you get exactly what we call a geodesic equation. If you look it up, you'll see exactly this, which is very cool because that means, yeah, if you take away gravity, you still have some ball which is constrained to some surface, but now there's no gravity, and just how it moves through this curvature is what a geodesic is. And so you can describe geodesics, which objects follow in Minkowski space, like with her talk, and things like that. So yeah, it's good. Yeah. I'm talking too much. Yeah. Yes.
Yes, I wanted just to comment that if we want to find some alternative and try to describe it as a Newtonian mechanics, then here there is some non-physical thing that our ball does not. So, for example,
Yeah.
if the surface goes down, the ball normally will jump. But here there is a constraint that the ball follows the surface. That is, there is some fictional force that we cannot describe easily.
The ball comes like this.
Force that forces the ball to go down and up together with the surface, and this force is really hard to describe in Newtonian sense. Well, when we are doing this Lagrangian formalism, we just describe how the kinetic and potential energy depend on the velocities and the position.
I think you'll
That's all, and then all formulas work because this is just technique.
You'll notice here, this ball starts right here, and physically, it might not actually wrap, or well, let me see if I find the spot where it does that. Change direction like this and wrap around this sort of pole. That's only because you're like on a roller coaster, and when you take a turn, you still have to stick to the surface. Kind of right here, I sort of drew it. If you have a pull that's upwards, you would expect the ball to just sort of roll up and keep going on its way this way. But because there's this fictitious force imposed by our constraint, it has to stick to the surface. It kind of has to go up for a second, spinning around it, which is very non-physical. It would detach, right? And then come back down. And that's something I had to sort of combat, right? And the way you would have to do that is change your, to consider this, you would change your holonomic constraint, which is just this equality, to an inequality. You'd make it greater than or equal to your surface, so then it can detach. But then you have to consider a lot more sort of piecewise dynamics when it's off and when it's on. Okay. And then you'd do collisions, and you'd get into what a lot of modern game engines do. Yeah. Okay.
I have a question.
Yeah.
So dynamical equations are four-dimensional. It means that you have two positions and two velocities.
Yeah, exactly.
But the energy is preserved. So because this magical force is always orthogonal to the trajectory, so there are no forces that eat the energy. So it will work. Only gravity makes work. So
there are like two.
It's okay. So then you need to have the conserved quantity.
Yeah, you have a bunch of, there's a few.
The conserved energy from this equation of motion.
There are a few first integrals of this system. Like you have momentum, angular momentum, energy. These are all conserved quantities, which if you sort of define what this is, and then use this equation to substitute into that equation and take the time derivative, it will come out as zero. Yeah, that's what we call a first integral.
But, so in this, I mean, in this four-dimensional system, so you have how many
Yeah.
integrals? 2, 3.
Well, here I've written it as the second derivative, but really we would define velocities, which are given by our first derivative, and then we'd have a basically a system of four equations which are first order. Right? Is that what you meant?
No, I mean, if you remember this theory about like rigid body and Euler ellipsoid.
Of course, yes.
So it is the motion of some complicated object reduced to two-dimensional motion.
Yeah. Oh, some phase space.
Because of the integral of the momentum, and maybe if you write here integrals and then use some maybe smart parameterization,
you can reduce the dimensionality. That's definitely possible, because we even saw before, like we put a constraint on, and every constraint we put on reduces the degrees of freedom by 1 or.
Yeah, but here still you have 4 variables, but they are related to the integrals, and maybe you can reduce.
Yeah, I think you could probably relate your horizontal even velocities with your maybe. You'd have to think about it.
Like have the energy constant, and through this constant, express one velocity through another, substitute here, and have less velocities.
Yeah, I mean, change of variables are always a very useful tool. Yeah. Good. Okay, thank you. Yeah. More questions we can talk like later. Yeah, after.
Yes, so thank you all everyone for coming today, and thank you for all our speakers, Natia, Zakaria, Noah. Please a round of applause for them again, please. conclude this talk, I would like to, first of all, as I already did, thank everyone for coming, for asking all these questions, for really paying attention to what our three students came up with. And I just want to tell you that you can take their places. If you have something in mind, something that you want to show research to the world, and you want to make, you have an idea in mind that you want to showcase it, and you want to make your CV better and have some actual research experience, don't hesitate, because I know a lot of people here maybe have the idea in mind, but I know it's very scary to take the first step. But you can ask Zakaria and ask Nacha, they're both first years, and they took the first step, and I hope they didn't regret. But so yeah, if you think about it, that's the first step. I'm sure it will be right. So if you're interested and have any topic in mind, or want to search for a topic, don't hesitate to apply for the potential fourth UGS that we'll do. And of course, as I said before, Math Society is always welcome to have any new, I would say, rightful minds in the board team to have interested in any part of the technical part or the design or any such thing, and you're maybe interested to, as I said before, make your CV even shine more. Don't hesitate to apply to join our board team. Thank you very much for coming today.